Hello, today we are going to be looking at the exam review for Unit 2, our Integers and Polynomials exam. First up, we've got these factor theorem problems. So we are given a polynomial function and one of its factors, and we are tasked with finding the other real zeros. So the real part is going to come into play with one of these answers later on. Now, with these, for most of them, we are able to use synthetic or long division, whichever your preference. I am going to go over how to do both kinds, and then from there we will factor or otherwise solve to find the other real zeros. So first up, let's take a look at 388 over here. We are dividing 2x cubed minus 9x squared plus 13x minus 6 by x minus 1. So what we're doing here is dividing 2x to the third by x, and our quotient here is going to be 2x squared. So then we take that 2x squared and multiply it by our entire divisor. So we will end up with 2x cubed minus 2x squared. Then we are going to subtract this entire row. I like doing it this way because this is how it mirrors subtraction in that step when you're doing long division with just integers. So we have negative 9x squared minus a negative 2x squared. So we end up with a negative 7x squared, and we'll bring down that 13x. So then we do negative 7x squared divided by x, and we end up with negative 7x. Multiply that by our entire divisor. So we end up with 7x, negative 7x squared plus 7x. We'll subtract that. So we'll end up with 6x minus 6. Divide 6x by x up here. And then we end up with plus 6 as the last piece of our quotient there. If you get a remainder that is not 0, I would go back and check your work, especially with the signs, because that is an area where it's easy to make some mistakes with, or just double check that you did some of the simple addition or subtraction correctly, because these are long problems. It's in the name, it's the long division, and sometimes we're so focused on that we trip up on some of the, 4 minus 2 is 1 or something silly like that. So now our quotient here is 2x squared minus, I'm not sure why it's doing that, so 2x squared minus 7x plus 6. We need to factor this and then set those factors equal to 0 using the factor theorem in order to find the other real zeros. So what we can do first is multiply 2 and 6, and we end up with 12. We look at our factor pairs of 12, and since this is a plus 6, we are looking for ones that have a sign that is going to be the same. So when we add them together, the sum is going to be negative 7. So we'll end up with 3 and 4. So we can separate that middle term. And it doesn't matter whether you do minus 3x minus 4x or minus 4x minus 3x. Either one is going to work out like this. And it will work out the same in the end. In each group, we are going to, when we're factoring by grouping, see if there's any common factor. So in this first one, we end up with an x we can factor out. And then what's left is 2x is 2x minus 3. And then what's going to happen in here, we can factor out a negative 2. And what's left is going to be 2x minus 3. If you're having trouble trying to figure out what you can factor out, your sets of parentheses on any of these that we can factor by grouping is going to be the same. So if you look at this and see, all right, well, I know our first set of parentheses is 2x minus 3. We can look at what can we divide out of both terms in that second group that is going to give us 2x minus 3. So then we factor out that 2x minus 3. What's left is the x minus 2 that's here and here. So then these are our factors. We set each equal to 0 according to the factor theorem. And we end up with our other zeros to be 3/2 and positive 2. Next, let's do one with synthetic division. So here we write down our 0 in this little box in the corner, and then our coefficients of our dividend across the top. We leave a space, draw a line, and first bring down the first coefficient. Then we're going to do some multiplication. So between -2 and -2, we end up with 4. Then we add what comes here. So 1 plus 4 is 5. Let's rewrite that. I'm not sure why the pen is not cooperating today. We do -2 times 5. We end up with a -10. Did I match these up correctly? No, I did not. So check your signs, everyone, because I did a sign incorrectly. I did the -2 because I was still thinking about changing the sign for the 0 for this. So our coefficients go 2, 1, -5, 2. 1, -5, 2. We bring down the 2. 2 times 2 is times -2 is -4. 1 plus -4 is -3. -2 times -3 is a positive 6. -5 plus 6 is a positive 1. -2 times 1 is -2. We end up with a remainder of 0. So that's a good example of some troubleshooting if you are going to end up with a remainder at the end, because this last term is our remainder, that is not 0, then you did something wrong. And as I usually say, it's probably a sign error. So what this looks like, this is 2x squared minus 3x plus 1. So let's see how we could factor that. Well, our only options for 2x squared of our factors are 2x and x. Our only factors of 1 are 1 and 1. And then since this is a positive 1, but it's a -3, these are both going to be negative. And if we looked at our outer and inner terms for FOIL, we have -2x minus 1x, which gives us a -3x. We set each of these equal to 0, and we end up with x is equal to 1/2 and x is equal to 1 as our other zeros. So for the next few, I'm going to go through with synthetic division. If you like doing long division, I am not going to stop you. That is your preference. There are some of the long division problems where you will have to use long division, like if our divisor is a second degree or greater term. Let's do some of these over here. So we've got 3, 1. Let's leave room for the 0. So we've got -3, 3, 1, -20, 12. Don't forget to leave a placeholder if necessary, like we'll need to do on 392. Bring the 3 down. -3 times 3 is -9. 1 plus -9 is going to be -8. -3 times -8 is positive 24. This sum is 4. We get -12. A remainder of 0. Great. So we have 3x squared minus 8x plus 4. So we multiply 3 and 4 and get 12. Our factors of 12 again are 1 and 12, 2 and 6, 3 and 4. Since this sign of the 4 is positive, that means our factors have to have the same sign, and they have to add, so they need to multiply to positive 12 and subtract to or add to a negative 8. So if you want to do this with slide and divide, it does work the same way with factoring by grouping with multiplying your a and your c values. And then, so we multiply the 3 and the 4, and we end up with x squared minus 8x plus 12. So we did the sliding. We factor this to x minus 6, x minus 2. And then we need to do the dividing. So since we had multiplied by 3, we need to divide each of these by 3. So our other zeros are going to be x is equal to positive 2, because we end up with x minus 2 as this factor here. And then a positive 3/2 here, because we have x minus 2/3, or you could also rewrite that as 3x minus 2. So you can do slide and divide, you can do factoring by grouping, whichever works best for you. Now, there are some of these, and for the length of this video, I'm not going to go through the work of all of these, but the answers will be on the key later on. If you end up with something that you cannot factor and that you would need to use the quadratic formula for, you can just leave. We will deal with the quadratic formula and finding other zeros later. And there are others that you will end up with x squared plus 4, which is going to give you no other real zeros. We will deal with that in our complex and polar unit. I just want to go over, before we move on to our modular arithmetic problems, take a look at what's happening with why this pen is dragging a little. Our long division here with our 2x minus 5 as our divisor, and our dividend needing some more space. Just to show some long division again, so we've got 2x cubed plus 5x squared minus 12x minus 30. So 2x cubed divided by 2x is going to be x squared. Multiply that by our entire divisor. Then we subtract. Watch your signs. So we should end up with a negative 5x squared minus 12x minus 30. Oh, it's just x squared. I knew something was supposed to work out differently. So just watch what you're multiplying by. I was still thinking about a different problem up here where it was 2x squared. So it should be plus 5x squared. That'll subtract to 0, so we have minus 12x minus 30. Divide negative 12x by 2x and get minus 6. Multiply negative 6 by our entire divisor. Subtract, we end up with a remainder of 0, which is what we should get. So then we have x squared minus 6 as our quotient, and that is a factor of our polynomial. That we can solve in two ways to figure out what our other real zeros are. One is if you just set x squared minus 6 equals 0, add 6 to both sides, and then square root. One thing about this is that you will end up with x is equal to the square root of 6, but sometimes people forget when we square root x squared, we have to look at both the positive and negative sides of this. So it should be plus or minus the square root of 6, so we end up with two real zeros from that. And that's part of the reason. The other part of the reason is I just love difference of squares. I know these aren't perfect squares, but they're still squares. We can factor x squared minus 6 into conjugates of x plus and x minus. Now, since 6 isn't a perfect square, what goes in this part of the conjugate is just square root of 6. Then we set each of those factors equal to 0, and we end up with square root of 6, and negative square root of 6 as our other zeros. Let's talk modular arithmetic. Remember, for modular arithmetic, we are looking at the remainder for these problems. So this first problem, 11 mod 2, is saying, look, we are taking 11, dividing by 2, what's the remainder? So 2 times 5 is 10, 11 minus 10 gives us a remainder of 1. 11 mod 3, same thing. 11 divided by 3, well, our quotient's going to be 3 with a remainder of 2. What happens if we have a negative number here? Well, I like to set these up with the quotient remainder theorem. So we have negative 11 is equal to, so our dividend is equal to our divisor multiplied by some quotient plus a remainder. It's just a long form way of writing out how division works. So we're looking at our multiple of 3. That is less than negative 11. And the key here is thinking about it as less than. And if it helps you to go through and look at something with like integers, like doing, all right, well, let's just say 14 divided by 3. Well, our multiple of 3 that's less than 14 is 12. It's going to work the same way with positive integers as well as the negative ones. So our multiple of 3 that's less than negative 11 is negative 12. And a mistake is looking at this as like, oh, well, it's negative 9, but negative 9 is greater than negative 11. So our quotient would be negative 4. That product would be negative 12. So then we'll add 12 to both sides and get our remainder of 1. That same thing is going to work over here. So we have negative 3 is equal to 7 times some quotient plus a remainder. And our multiple of 7 that's less than negative 3 is negative 7. Add 7 to both sides, and we get our remainder to be 4. So negative 3 mod 4 is congruent to, or negative 3 mod 7 is congruent to 4. Now, 231 mod 5, we divide 231 by 5, and we know that our remainder is going to be 1 because 230 is a factor of 5. We need to know how to convert numbers to and from base 10. With all of these problems, we need to be able to find our different place values. They are always going to go base to the 0 power, base to the first, base to the second, and I just put the lines so we have somewhere to show. You don't have to put them. It's up to you. It's just like we have our ones place, our tens place, our 100s place, our 1000s place, 1000s place. We'll talk about our 1000ths place later. So compare everything to our base 10, our decimal system. It's going to be set up in the same structure. So hexadecimal is base 16. So we have our ones place, our 16s place, and our 256th place because that is 16 squared. So then what we're doing when we're converting to base 10, we want to multiply. So we take the number that's in a place and multiply it by the place value. In hexadecimal, in base 16, we use letters to represent numbers that are 2 digits, right? So like A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. If we hit 16, then that bumps us up into the next place value. So for 256, we have 11 of them. So we do 256 multiplied by 11. Well, that's going to be 256 plus 2,560. And this is also nice to look at when we're dealing with multiplication because we're going to look at it in different bases set up with the same structure. So we have 2,816 coming from the 256th place. Then we have to add that to 16 because we have 1 in the 16th place. And then since a is 10, we need to multiply 10 by 1 because there are 10 ones. So we add all this together, and actually I'll just do it here. So 6 plus 6 is 12, but 12 is greater than base 10, so we represent that as 110 and 2 ones. 1 plus 1 plus 1 plus 1 is 4. So it's 2,842 in base 10. Taking a look down here with our eights, our base 8, so we have 1 1 and 2 8s. So we do 2 times 8 plus 1 times 1. So we end up with 17 here. In our base 5, we have our 1's place, our 5's place, and our 25's place. Because moving to the left, we are just multiplying by whatever our base is for the place value. So we have 25 plus 5 plus 4. So it's going to be 34. And then for base 2, we've got our binary, 1, 2, 4, 8, 16. And the thing is to just make sure you're multiplying by 2 each time. A common mistake I see is somehow having a 6's place in there, or if people think they're squaring it, we end up with 1, 2, 4, 16, 256, but it's multiplying by the base, just like in base 10. So we have 16 plus 4 plus 1 is going to be 21. Now, going the other way, looking from our decimal system, from base 10, into a different base, we need to end up dividing. So we set up our place values. So base 2, we've got our 1's place, our 2's place, our 4's place, our 8's place, our 16's place, our 32nd place, and we do not need our 64th place because 64 is greater than 34. Then we do division. 34 divided by 32. We write our quotient here, so our quotient's 1, our remainder is 2. Then that remainder becomes our new dividend, and so we do 2 divided by 16 is 0, 2 divided by 8 is 0, 2 divided by 4 is 0, 2 divided by 2 is 1 with a remainder of 0. So it's 1, 0, 0, 0, 1, 0 in base 2. Sorry, that is a sloppy one. I'm trying the best I can with the pen not quite cooperating. 45 in base 3. Let's set up our place values. We have our 1's place, our 3's place, our 9's, and then our 27's. We do not do more because our next place is 81, which is greater than 45. Remember, in base 3, we're allowed to have 0's, 1's, and 2's. So 45 divided by 27 is 1 with a remainder of 18. And then 18 divided by 9 is 2 with a remainder of 0. So we have 1, 2, 0, 0 in base 3. So 243 in base 16. So we've got our 1's place, and then our 16's place, our 256th place. Okay, that is greater than 243. So we know that 16 times 16 is 256. Well, so 16 times 15, that product we know is going to be 16 less than 256, so it's going to be 240. So we are going to have 15 16s with a remainder of 3, so there are 3 1s. So we have 15 16s and 3 1s, but we can't write that as 153. That's not clear, and it makes it look like the 1 is in the 256th place. So instead, what we do is represent 15 with F. So it is F3 in base 16. So representing 16 in base 8, We've got our ones place, our eights place. 16 divided by 8 is 2 with a remainder of 0. Oh, look. And that's all we need to do there. Then 153 in base 7. So we have our ones, our sevens, our 49's place. So 49 times 3. $147. So we have a remainder of 6. So we have three 49s, 0 7s, and 6 1s, because 6 divided by 7 is 0 with a remainder of 6. So we have 3, 0, 6 in base 7. So converting from different bases into base 10 is multiplication. Converting from base 10 into other bases is division. Now we're going to take a look at a few different types of operations in different number systems, talk about radix points, and then we will go over in general how to do a few of these, but then the rest will be just on the key. They'll work out the same way as they do the ones that we do on the video. So we are looking at this in base 7. Our addition is going to work the same way that it would work in base 10. So like 5 plus 2 is 7, but that 7 can't be represented by a 7 in base 7 because only 0 through 6 exist. So that bumps us up into the place value. Next place value, we want to think about, well, how can we write 7 in base 7? So we've got 1 7 and 0 1s. 1 plus 2 plus 4 is 7. Again, 0 1s and 1 7. 1 plus 6 plus 3 is 10. So how we write 10 is we have 1 7 and 3 1s. So it's just like when we were adding before and we ended up with 12. 12 is greater than 10, so we'd have 1 10 in the next place and then 2 1s. Let's do the same thing in binary over here. 1 plus 1 is 2. 2 is 1 2 and 0 1s. 1 plus 1 is 2, which is 1 2, and 0 1s. 1 plus 1 is 0 1s and 1 2. 1 plus 1 plus 1 is 3, and we write 3 as 1 2 and 1 1. Try not to get the little tail on there. Great. Now this, don't be intimidated by a radix point. It's what we call a decimal point when we're looking in different bases. We will talk about that later. Let's just do our addition for now. 2 plus 2 is 4, but 4 in base 4 is 1 4 and 0 1s. 1 plus 1 plus 0 is 2. 2 is allowed in base 4, so that's fine. We just write 2. 1 plus 3 is 4, which is 0 1s and 1 4. 1 plus 2 is 3. Now this number, 30.2, we've got our ones place, that's not a 7, our ones place, our fours place, so our whole number value with this is 12, but the 2 is in the 1/4 place. Think about after the decimal point in base 10. We have our tenths place, so it's 1/10. Then we have our hundredths place, so 1 100ths. 1 100th. So if we look at that as a base, it's 10 to the negative first, 10 to the negative second, and so on. So that's how it's going to work with all of our different ones. So 4 to the negative first is negative 4. So this is, if we're looking at this in base 10, we do the same thing we do with ones without a radix point. So just our integer values where we're multiplying the place value by the number that's there. So 3 times 4 is 12, 0 times 1 is 0, 2 times 1/4 is 2/4, or you could write this as 12 and a half if you wanted to do it in base 10. Let's see some subtraction here. So with the subtraction, it's going to work in the same structure as base 10, where some subtraction works out fine, And then others, we need to do some borrowing, but the borrowing is going to follow the same structure, just work a little differently. Like we cannot subtract 2 from 1 here. So we need to do some borrowing. Just like in base 10, we subtract 1 from the 2. Because what we're doing here is taking one of those two values that's in the 3's place and breaking that up into 1's. So this is going to be a 4 because we're adding 3. I know in base 10 we just kind of put like a 1 next to it and then, oh look, that's 11. What we're actually doing, the mechanics of it, is adding 10 to each one because 10 is the base. So you end up, when you borrow, adding whatever the base is. So then we can just subtract 4 minus 2 is 2, 1 minus 1 is 0, 1 minus 0 is 1, 2 minus 2 is 0, 1 just comes down, and it's going to be a 1. So the borrowing, subtract 1 from the previous place, add whatever the base is to the next value. It's going to work here. So 3 minus 7, we're in base 8. We go through. We have to borrow here, but then we add 8 because that's the base. So this is 11. 11 minus 7 is 4. We can't do 0 minus 7, so we need to borrow. So this becomes a 3. We add 8 here. 8 minus 7 is 1. We cannot do 3 minus 6, so we need to borrow, but we can't borrow from the 0, so we have to go to the 7 first. So 7 becomes 6. We subtract 1. Turn this into an 8, but because we've added 8 to the 0, but then we need to subtract 1 to make it a 7 so that we can add 8 to the 3 so that we can do 11 minus 6 is 5. Then we get 6, 7, 5, 1, 4. This one does not work out, so don't worry about it. Then let's talk about multiplication, because the other addition and subtraction ones will work out very similarly, and we can actually do this base 16 one as well. And don't worry about this one. It's a non-calculator exam, and this is going to be a very large number. So let's deal with multiplication. So 1 times 0 in base 2 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. See, multiplication's easy. No. The 1 is the multiplicative identity in any base. So 1 multiplied by any number is itself, whether we're in binary, decimal, octal, hexadecimal, whatever. Let's look at one that's going to be a little more work. So we are in base 6 here. We'll start out by multiplying this 4 by each of the numbers in the top. So 4 times 4 is 16. But we can't write a 16 like we would in base 10 because that's not how it works here. We need to think about it as the reason we write that 16 in base 10 is because we have 1 10 and 6 ones. How do we write 16 in base 6? So 16 in base 6, we've got 2 6s, because 2 times 6 is 12, with a remainder of 4. Then we do 4 times 3 is 12, plus 2, just like when we're multiplying in decimal. So 12 plus 2 is 14. So how do we write 14 in base 16, or in base 6? So that's going to be 2 6s and 2 1s, because 2 times 6 is 12, plus 2 is 14. 4 times 5 is 20, plus 2 is 22. But 22 in base 6 is 3 6s, gets us to 18, and then 4 1s. Next up, we take the 1 and multiply it by each of these values as well, but we need a 0 as a placeholder because that 1 is in the 6's place in this case, not the 1's place. So then we have our simple multiplication because 1's easy to multiply by. Then we need to add. 4 plus 0, still 4. We need to follow our base rules here as well. Like 2 plus 4 is 6, but 6 is 1 6 and 0 1s. 1 plus 4 plus 3 is 8, which is 1 6 and 2 1s. 1 plus 3 plus 5 is 9, which is 1 6 and 3 1s. So our product here is 1 3 2 0 4, all of it in base 6. Let's just do this subtraction one before we do some of those word problems, and the other ones will work out the same way with these operations as we've done previously. So we're in hexadecimal, so this might look a little more intimidating, and if it helps, right at the top of each of the papers what these values are. So 3 minus 0, 3. Easy enough. A minus F is 10 minus 15. Can't do that. Need to borrow. D becomes a C. And then we have to add 16 because we're in base 16. So this is going to be a 26. So then we have 26 minus F, which is 15, gives us 11. But 11 is B. We can't do C minus E because it's 12 minus 14. So we need to borrow from this. This becomes a 5. And then C is 12, we're adding 16, so this is 28. We can't normally have 28, but we're just doing it temporarily before we do the subtraction. So 28 minus 14 is 14, so this is going to be another E. We can't do 5 minus 7, so we need to borrow. 5 plus 6 is 21. 21 minus 7 is 14, so yet another E. Last up for the video is some modular arithmetic word problems. So students are boarding buses for a trip to the beach. 567 students and 45 students fit on a bus. How many will be left behind if only full buses leave? I understand with some of the word problems that we need to suspend some disbelief, like those where you're in elementary school that you might have seen of, two students talking about their piles of 567 apples. And this, we know that we're not leaving students behind. This, we take our total, 567, we're doing mod 45, and we need to look at the remainder to see how many students are being left behind. So what we can do is divide 567 by 45. We have 450 is 45 times 10, and then add another 45, and then so that's 495. Add another 45 is 540. Okay, any more would take us over. So 540. 567 minus 540 is going to be 27 is our remainder. We don't care what the quotient is. We just care about the 27 students who will be left behind. What time will it be? 314 hours from 1 p.m. Since we are looking at 1 p.m. for time, we are going to do mod 24. So we have 314 hours. We're doing mod 24. So we just need to, we can do the same thing. So 24 multiplied by 12 gives us 288. By 14 or by 13 gives us 312. So our remainder here is going to be 2. But 2 isn't our answer. We are looking at what time it will be. We need to not just do the modular arithmetic, but answer the question. So 2 hours from 1 p.m., we just add that on. Then if we were looking sometime in the past, we would just do like negative 314 mod 24. If it was just asking for like a clock that doesn't have AM or PM, we'd do mod 12. Day of the week will be 841 days from Wednesday. Well, we need to do 841 mod 7 because there are 7 days in the week. So we do, let's do some long division here. And we get a remainder of 1. So that is going to be 1. We can set up our week, Monday through Sunday. And since this is Wednesday, Wednesday would be R0, Thursday R1, Friday R2, and so on. But since our remainder is 1, it is going to be Thursday. All right, the rest of this key will be available on OneNote. So thank you for watching.